Dear students, let us continue our video lectures on machine learning for image processing. Let us resume back to our discussion on neural networks. In the last class, we have discussed about artificial model of neuron. We have seen the similarity between the biological neuron and artificial neuron. We also have noted an analogy between some of the aspects of biological neuron to artificial neuron. Let us continue our discussion there and let us see the limitations of artificial neuron, and then let us discuss about neural network, the need of neural network. I'm sharing the screen. So in the last class, we have seen that a biological neuron has neurotransmitter substances that are transmitted from each of the several neurons to a neuron that under consideration. And these neurotransmitter inputs comes as information from different neurons to a neuron under consideration. Okay, so under the neuron in consideration. So, and then this information is something like similar to the feature inputs that we have. And the inputs from different neurons will not be taken equally. There are some synaptic strengths that will determine the weight or the relative importance to be given to each of these inputs. And that we consider as relative weight that we need to give to each of the feature inputs. And the assimilate to some of these weighted features inputs is what is taken as input to the at the axon of the neuron to take a decision with its own bias. Okay, and then this is being weighted by an activation function to trigger or not to trigger. Okay, so and we have seen that this model is exactly like relating the decision output variable yk to input variable xk or input features xk through this equation yk equal to f of w transpose x plus v. We also have noted that if we consider this f as a sign or a threshold kind of function, then what the role of linear perceptron, what linear perceptron is doing, putting one side of the samples to one class, putting the other side of the samples to the decision boundary to other class is exactly same as what this model of neuron is depicting. So a simple model of neuron, okay, is same as linear perceptron, and learning whatever we have discussed for linear perceptron is essentially the basic algorithm for learning a neuron. Okay, so now given this, let us now proceed to see what this neuron can do and what are the limitations of this neuron, model of neuron. So here we have seen this as the model of neuron in the previous slide, and these are all the feature inputs. Input features. Okay, so given these feature inputs, what we are doing, we are weighting them and then taking the collective weight as the net value, and this is being triggered or not being triggered by an activation function. As we have discussed, f is referred to as activation function. This is ideally a non-linear function. Okay, given this, the output depends upon the input like this. And what we do for training a neuron is, if we have set of samples d coming from x1, so if x1, x2 and so on up to n samples, xn, so among them half of them or some of them may belongs to class 1 and some of them may belongs to class 2. Okay, so given this, what we want to do is to keep inputting each of the samples xk from one of the class. Xk may belongs to either omega 1 or omega 2. Fine. And when we input this, we get an output yk. Okay, this yk maybe see if I initialize randomly these weights, what will happen? The random initialization of these weights initially will not make the appropriate classification feasible. So what I'm discussing in this slide is now learning of a neuron. As we have discussed, learning of neuron is exactly same as learning of linear perceptron, but I'm trying to give here a real picture with when we have large number of samples and we want to perform two-class classification with the neuron, model of the neuron. Okay, so now what we do is we keep inputting these samples. So as some xk from xk is taken from belongs to set D, fine, and usually we input them, we throw a random number between 1 to n, and a random sample is taken and that is given as input. So if say what ideally should happen is, so if xk belongs to class 1, the label has to be, say for class 1 label has to be +1 and class 2 label has to be -1 or 0. Okay, this if xk belongs to class 1 and if xk belongs to class 2. Okay, so this ideally should happen, right? But because of random initialization, initially w, which is equal to w1 to wd here. So please make a note that this is d in our case. Okay, we are taking up to d dimensions. Okay, so each of the xk is belongs to d dimension. So xk belongs to d dimension. Please, x1, xt, right? Okay, so xk1 to xkd if we want explicitly to specify, right? So when we randomly initialize, we will see more systematically the range in which we have to initialize and which kind of random distribution we have to follow to initialize these input weights. But let us, for time being, assume that they're randomly initialized and uniformly randomly initialized between some -1 to 1 and so on. Okay, so and then when we randomly initialize, say yk may not be belong to 0 or may not be belongs to 1 for all class 1 samples. Similarly, will not be equal to -1 for all class 2 samples, right? And this is natural because we randomly initialize it. So this is step 1 is to initialize the model. Here model means the neuron, okay, or the linear perceptron. Now learning of neuron is same as we discussed. This step 2 is learning of neuron. What do we mean by learning of neuron? Learning of neuron means identifying the weights that are more appropriate such that all omega-1 class samples, okay, when I give at the input, they belongs to omega-1. All omega-2 samples, when they are given as input to the model, okay, we get classified to omega-2 class. That means learning of model means learning weight vector, okay, or identifying appropriate weights. Arriving at the appropriate weights. What do we mean by appropriate weights? W star, after we learn it, okay, the learned weights, okay, W star will enable us to put, okay, Yk, which is equal to F of W transpose, this is W star transpose, Xk plus B, okay, all class 1 samples. If I give Xk belongs to class 1, if it is very well learned, it implies that Yk is equal to 1 or W transpose Xk plus B is greater than 0. Okay. Similarly, if Xk belongs to omega 2 class, it implies the network has to output -1. Okay. Or if it outputs -1 only when W transpose, okay, Xk plus B is less than 0. Okay. So this is what is ideally expected. Now the question is, when this happens, okay, or how to make this learning happen. Now you can see that this is exactly same as what we are learning or doing in linear perceptron. Thus, learning of neuron is same as learning of linear perceptron. Okay, that is discussed. In fact, the linear perceptron, the earlier name of neuron itself is linear perceptron. Okay, so now this linear perceptron learning, if you want to write it here, rewrite it here, how should I write W? So we update W from the raw initializations in each iteration. How do we update? You making use of a predefined error and the gradient of error with respect to the current W. Right? And this is referred to as gradient descent rule. So we will make use for this a predefined error. What was the error we have defined? Delta K W transpose Xk. Okay, this is what we have defined, where Xk are misclassified samples. Gather all the misclassified samples either from class 1 or class 2. Okay, and then we measure its distance with respect to the separating line, that is W transpose Xk, and multiply by a constant delta K, such that delta K is equal to -1 for samples, okay, for omega 1 class and equal to +1 for omega 2 class. This is just a constant to take care of the error irrespective of signs. Okay, the modulus of error or the error quantity of error, quantification of error without sign. Okay, and then this summation over all misclassified samples either from class 1 or class 2 put together will enable us to calculate the total error. Please note that this J is a function of W, the weight vector, and the dou Z by dou W is the gradient of weight vector at given weight vector W. And this expression is being suggested by learning of perceptron. This learning rule of perceptron is being suggested by gradient descent. Okay, is the guiding principle by which we are writing like this. Once we do this, how many times should we do this? So I iterate it till we identify. So we keep computing these two. Okay, and then based on this, J keep changing. Once we change the decision boundary or once we change the W, J will change. And once we change the J, the error will change. Okay, and then these ones, we do this for several iterations. What we see is that, okay, the weights doesn't change. If the samples are linearly separable, we will arrive at a decision boundary where we can easily separate class 1 and class 2 samples. And that's where we say that the learning of neuron is done, or we have arrived at W which will put all the samples of class 1 to one side and class 2 to other side. Okay. And hence the convergence rule is if WT plus 1 doesn't change, minus WT, okay, is very small. Or in other words, dose A by dou W is less than an epsilon. The gradient with respect to the weights for the cost function doesn't change. That means you arrived at a constant slope. Okay, the learning is complete. Okay, learning is done. Okay, and the length model means the weight vector. Finally, what this results? Okay, this results in W star, a length weight vector. Okay, and that's what we have used here. Okay, in making use of final decision. So that one is, so once we do this, what we have is length weight vector with us, and we can take a decision with respect to that in testing. Okay, this process, this whole process, this learning process is referred to as, okay, training. Okay, and once you train with all like this, what we finally get a ring of neuron will enable us to find out W star. Okay, and with this we can test and see if all the class 1 samples and class 2 samples are correctly classifying, or how much is the accuracy of classification. So if we now say, for example, want to test it, so assume that now we have got xk again. So another set of samples, k equal to say 1 to nt or 1 to p. Okay, let this be test samples. Now, if you want to test them, what we do? We give these test samples xk to a model of neuron. This simply the model of neuron can be depicted like this. Okay, so this is input xk, and what is this is neuron. So, and this is output yk. Okay, so what we have here, the length neuron will have weight vector with it. So we can consider here weight vector. Okay, so what yk is equal to f of W transpose xk plus b. So please note that in ideal case, even we can absorb this. This is xk dash and w dash. Okay, we can even write like this. As you know, an extended w and xk can also be done by xk dash is equal to xk and 1, and w dash is equal to w weight vector and b, putting together. Okay, fine. So now let us see this. When you test them, all of them may not be correctly classified. The class 1 samples may be put into the class 2 by the length model even, and that accounts to classification accuracy. Okay. Now the questions here are, see, what kind of activation function? Okay, what kind of activation function or nonlinear function should be used? Is preferred. Okay, so this next question is how to initialize the weights W naught. Let me write W of 0. Okay, the next question is what kind of problems, okay, what are classification tasks? What classification tasks does this neuron can do, and what classification tasks neuron cannot do? Single or simple neuron can solve, okay, and which it cannot solve. Okay, so these are all the questions to be addressed. Fine. And anyway, since we have come up with one learning rule, let us stick to that for time being. We will see if there are any limitations even with this learning rule, and see to improve this learning rule later. Okay, so now given this, let us start with the last question. What kind of classification problems this can a single neuron can solve? Say assume that I have some samples. So let us create a hypothetical case wherein I have two features, x1, x2, and sample 1, sample 2, sample 3, okay, sample 4. 4 samples with me. Okay, and the problem that output assume that I get from the AND operation between x1 and x2. Let these x1, x2 be binary features, and y equal to x1, okay, and x2. X2. So, and let us put okay. So fine. So now this is the logical AND operation. So let this be 0, 0. So y is 0, 0, 1, y is 0, 1, 0, y is 0, 1, 1, y is 1. Okay. So now the question is, can this classification, let's assume that we are giving only 4 samples and we want to find out the labels. That means we want to map this to class 1 and these 3 to class 2. Okay. So can this task be performed by a simple neuron? That's the question that is asked. Let us see it, since it is a 2-dimensional case where you have only 2 features, x1, x2, and this is a simpler case, only few samples. We can easily plot and sketch and see. The first sample is here. Okay. The second sample is here. Third sample is here. And fourth sample is here. Okay. 0, let this be, this is 1, 1, and so on. Okay. So as you can see, I have plotted the samples based on x1, x2, their features. Okay. And then I have put intos for omega 2 samples and circle for omega 1 class sample. Okay, as you can see, this is omega 1 sample and these two are omega. So can this be solved by the linear perceptron or by a neuron? That's the question. The answer is yes, because there is, see, if you start with even some arbitrary separating line, if I start with this separating line, what shall happen? This is the misclassified sample. Okay, if I put that, okay, this is the, so all this side is positive, okay, and all this side is negative. So this is omega 1 class for this and this is omega 2 class. Okay, I see that this is misclassified. So this line gets adjusted in the next iteration and I will be able to figure out, I will be able to come up with this as the converging line or converging decision line with the updated W. Okay, this is W1. Okay, and this comes from W0. Fine. As you can see, this W0, if we okay, this is W0, direction of W0. Okay, and if we strictly want to do W0 transpose x plus b equal to 0 is this line. W1 transpose x plus b is equal to 0 is this line. Okay, and for this, what we have done for this, okay, this sample, which is misclassified sample, okay, is being added. Okay, and after that, what we have? Given this and this, we have a okay, algebraic sum of them will give rise to nu W, something like this. Okay, and this is what is the nu W. Okay, this is what we have got after adding algebraically. Okay, this xk, misclassified sample xk, and W0. These two are added to get this W1, right? As you can see, right? So, right. Right. Okay. So now we are able to separate them after one iteration, or after a couple of iterations, we will converge, and there is a separating line that separates class 1 and class 2 samples here. As you can see, these three are class 1 and class 2, and this is class 1. So you can separate them by separating line because they are linearly separable samples. This implies that a perceptron or a neuron can separate linearly separable samples. Separate means classify. Okay. Now let us see another example. What are the limitations? Can you guess before we move on to the next example? However, fail to classify non-separable samples. Because we are looking at a linear decision boundary here. Even if we consider other than threshold activation function, still what will happen? All W transpose X plus B, if it is higher, are put into one class, or lesser will be put into another class. Okay, so because of that, this F, as we will see later, has a property of monotonic function, monotonically increasing function. Okay, so because of this, the reason for putting it as monotonically increasing is, see, the collective inference, if it is higher, then those have to be put into one class. Collective inference being lower, it has to put into another class. Okay, so we cannot underweigh the weighted sum of that we have expressed of the input features. So, and that this is monotonically increasing function, and if this is monotonically increasing function, okay, we can only perform a linear classification of separable samples. Okay, we can only separate if the samples are linearly separable, okay, from class 1 and class 2, right? And this is known to be a very important and great limitation of neuron. Okay, let us see that with another example. See here, if we take now the XR problem, here let the samples be this is sample 1 and sample 2, sample 3 and sample 4. These are samples. And what we have here are features. So let me write okay, these are features. Okay, these are features and these are samples. Okay, so now given that, what is this? How O is our Y, YK. So this is actually XK. The feature vector say X1 is equal to 0, 0. Okay, similarly, the second sample is 0, 1, and so on. Fine. So, and these are the Y output labels. As we can see here, these two can be belongs to omega 1 class, and these two, say the sample 1 and sample 4 belongs to omega 2 class here. Okay, so as can be seen from the output variable YK or O, right? Now given this, if we sketch them, please see that this is the first sample. Let me put the sample indexes. Okay, this is the first sample, sample 1, and the sample 2. Okay, and then third sample. Where is it? Oh, sorry. This is second sample, this fourth sample, that is 1, 1. And the second sample is 0, 1, that is sample 2 and sample 3. Okay, as you can see here, sample 2 and 3 belongs to omega 1 class, and sample 1 and 4 belongs to omega 2 class. So this is not linearly separable problem. Okay, so you can't separate them by a single line. Now the question is, and hence a neuron will not be sufficient to classify them. Okay, so what we want to do now is, what should we do? When a single neuron will not be able to classify, what do is, we construct a network of neurons and together see if we can classify them. Okay, and there comes the concept of neural network. We construct this is an example of a small neural network where you can see each is a neuron, right? So as you can see, a neuron is typically depicted by a sigma sign with F. Okay, you can consider either like this or you can separate them. As you can see here, they have separated this, and this is what is shown as the activation function, threshold activation function. Okay, so this is another small representation of a neuron, and you have one neuron, two neuron, and a third neuron here. So these are organized in some sense. So when you want to construct a network of neurons, several questions emerges. What questions? Say how they should be, how neurons has to be arranged or organized, or how the architecture of neural network should be. So that is, how should be the architecture. Okay, then how should the connections between the neuron be? See here, as you can see, this neuron and this neuron are connected in like this, and this neuron are connected, and this neuron has no connections with other neurons. Okay, and this connection can be there or need not be there. Okay, and similar is the case with this. So how the connections should be? Okay, how should be the interconnections? Fine. This also can consider as, this is the arrangement of neuron and this is the connections between the neurons. This also comes under under architecture. You can consider under architecture. Okay, design of architecture, right? And then how the weight should be initialized, how the activation functions or the nonlinear functions. Okay, all these questions still persist. How connection weights. Okay, what activation functions to use. Okay, and further, what loss function and learning rule. Okay, these are all important questions. What kind of loss function and learning rule to be used to train this network? Fine. So these we need to see again in the context of neural network. See, before we do all that, let us assume that we are given a nice neural network, which is shown here. Okay, and with some initialized weights. Okay, so this is the neural network given with some initialized weights. See, let the weights be. See, this x1, x2 has, say, let us consider x1, x2 are inputs. The net1, net2 are corresponding outputs. This output 1 is equal to, say, let this be equal to y1 and this is equal to y2. Okay, and this output be equal to z. The final output what you have here. Okay, so now what we want to see is how does y and y1 is connected to x1, x2. Fine. Given that this is equal to, say, some w11, that is x1 to x2, w11, and this is w21, that is x1 to y2, right? x1 to net2 otherwise. Okay, similarly, this is equal to w12 and this is w22. Okay, so these are the weight elements that are given, right? Given this, and these are biases. This is B1 and this is B2. Sorry, bias, right? This is bias B2. Okay, so given this notation, we want to see, okay, how the output is related to input essentially. Before that, we want also to see how the net1, net2 are related to x1, x2, w11, w12, and so on. Similarly, we want to see y1, y2, how they are related. And then subsequently, we also want to see this z is related to y1 and y2. So these here are again biases. This is bias B, let this be. And then this is W. Okay, W1, W2, and W1. Just for simplicity, W1. Okay, so now let us see this. So Y1, if I want to write, say what I write Y1, please note one aspect more clearly, remaining we will be easily able to write. Y1, if I want to write, how should I write? So please note that Y1 essentially is equal to f of, okay, activation function, let this be f. Okay, so this also activation function anywhere is f. So f of net1. And what is net1? Net1 is nothing but x1 into w11 plus x2 into w21 plus b1 bias. Okay, so x1 into w11 plus w21 into x2, right? Sorry, w12 into x2 okay, based on whatever we have put here, w12 into x2 plus B1, right? So essentially net 1 is this. So similarly, you can write here. See, let us substitute and write explicitly so that we will easily relate to the whatever the details that are here in the slide, right? So let us write f is an activation function. Please note that, and this is a threshold activation function. X1 is how much? X1 is X1 only. W11 is 1. X1 plus W12 is again 1. So it is X2. B1 is minus 1.5. So this implies that this is what is Y1. And hence, here please note that net 1 is equal to X1 plus X2 minus 1.5. And okay, if net 1 is greater than 0, Y is equal to Y1 is equal to 1 if okay net 1 is greater than 0. Minus 1 else, right? Greater than or equal to 0. Okay, this is what we have from the threshold activation function. Okay, here they have put if it is negative 0, but let us put minus 1 for our benefit. Okay, so based on the whatever table we have written, let this be minus 1. Similarly, let this also be minus 1. Okay, right. Okay, so now let us see the other details that are shown in the table. Similarly, what net 1 I have written here, x1 plus x2 minus 1.5. y1, as you can see, it is f of net 1. When this is negative, this is minus 1. When this is positive, this is plus 1. Okay. Similarly, net 2, what is net 2? Is equal to x1 plus x2 minus 0.5. That's what I have written here. F of net 2. What is z or what is net, for example, here? Net is equal to y1 into minus 1 plus y2 into plus 1 minus 1.5, whatever I have written here. And then this is f of net. Okay. So now given these samples, which are exactly XR samples. Okay. So what I have calculated is what these network outputs. We want to see if this network can classify these two samples into one class. Okay. And the remaining two samples into another class. We are looking at all this. We have seen that a single neuron cannot classify them properly into two classes for the labels that are given. Okay. We have constructed a small network of neurons and we want to see if this network of neuron is efficient enough to classify them into respective classes. If so, we say that the neural network has a power to make even non-linear decision boundaries. Right? So we want to see that. Okay, or we want to see for this given weights and so on, whether this classifies both to one class, these two samples to one class and these two to another class. Right. You can consider now writing the, say, put this in the expression. You will get minus 1.5, minus 0.5, minus 0.5, and 0.5 here. Right. Based on this, I have written here, okay, minus 1, minus 1, minus 1, plus 1. Because f of net is plus 1 if it is positive, minus 1 if it is negative. Similarly, this x1 plus x2 minus 0.5 net 2, if you calculate for these input features, what you're getting are these values. And thresholding will give these values again. Positive means plus 1, negative means minus 1. Now, given this y1, y2 information, we can calculate the net by minus y1 plus y2 minus 1.5. Now, you can see that if you make a threshold activation on the top of the output, net output, you are able to see that the two samples are put into one category and other two samples to other category. This means that a neuron doesn't have a power to make nonlinear decision boundaries, but however, a neural network has the power to make nonlinear decision boundaries, right? That's what we have seen in this slide. And this is the network which you can see is a nice example of making nonlinear decision boundary. Okay, so you can see that this is one region R1, this is another region R2. That means it has made piecewise linear, but overall it is non-linear decision boundary. Correct? So now let us see how it made this ability to do it. So in this figure, you can see that if you consider a single neuron, okay, so each of the single neurons are outputting one Y, right? So as you can see here, Y1, Y2, here also, you can see that the output what it gives is Y1. Okay, the output this gives is Y2. Okay, so now if I sketch them, say Y1, so with features X1, X2, if I make a plot of Y1, okay, with features X1, X2, I see that it is just an activity of a single neuron, and hence this is still a linear decision boundary. Similarly, if I make a plot of Y2 alone, this is also a linear decision boundary. But now, giving the output from two neurons to third neuron now is able to make a nonlinear decision boundary by algebraic combination of these two, right? So that's how the neural network has the model to make nonlinear decision boundaries, right? So, and this is the motivation for the design of all neural networks. Okay, so now let us come to a little bit of terminology of neural network. We have seen that the power of neural network is that it can make nonlinear decision boundaries, while a single neuron is not capable of doing it. Okay, now the question is, see, if this is able to do, what are all the things we need to figure out in this to make this happen? See, as we discussed, first thing is architecture. Okay. So what kind of architecture should we have? See, usually the well-known and widely used and simpler architecture is feed-forward neural network. That means, as you can see here, each of the layer, okay, gets feed-forward inputs, okay, to next layer, or each of the layer will get a input from previous layer. Okay, so these connections are all goes in forward direction. Okay, and these are all connected. This is referred to as feed forward neural network. Okay, if you have a set of neurons, and if you have some other set of neurons, and if you have some set of neurons in another layer, each of the neuron or of previous layer gets connected to each of the neuron of next layer. Okay, that is referred to as feed forward neural network. Okay, so each of the neuron gets connected to all other neurons. So just for simplicity, let us ignore these things, okay, to make a simpler network. Here, similarly, you will have actually connections to all this. And this is the output. Okay, you can have single output, or even you may have multiple outputs. Okay, so this is a typical feed-forward neural network. So now, please note that if we have, say, x1 to x3, three inputs here, three input features, and y1 to y2, two hidden outputs, and z1 and z2, that is output variable. So input variable is x1, x2, and x3, right? And hidden this is referred to as hidden variable, y1, y2, and the output variable o or Z is Z1, Z2, right? And this is, as I mentioned, this is referred to as input layer. Okay, so the variables where we input is input layer. See, usually the activation function is shown like this. This means that we are just doing linear activation, or we are just whatever is the input value, we are giving it as output of this neuron. Okay, so here if I show something like this, it means that it is a threshold activation function. Okay, so I am putting the positive ones to one side, negative ones to other side. Okay, so if I can show different, we will introduce few more activation functions shortly. Okay, for time being, this is good enough. Okay, so now okay, fine. Now let us see how the outputs in the hidden layer are connected to outputs in the input layer. Right? So see here, as you know, y is anyway a function of net. So net1 in the previous example you have seen, net1 is equal to w11 x1, right? So y is equal to f of net, right? And net2. So what comes here as output immediately is net values. So net1 is equal to w11 into x1 plus w12 into x2 plus w13 into x3. Okay, if you have, since you have 3 here. Similarly, net2 is equal to w121 into x1 plus w22 into x2 plus w23 into x3. As you can see here, net1 and net2, if you consider as a net vector, this essentially comes from a matrix multiplication of x1, x2. Now I have left here the biases B1 and B2, but we can consider them at later point of time. With 1, if we add here, bias also will come into picture, right? So now how do we bring in W11, right? Also X3 is also there, third input and 1. Putting all these things together, X3 and 1, right? So W11, W12, W13, 1, B, okay, B1, W21, W22, W23, B2, right? So its instance net is equal to W times X. Okay, so you can see with this kind of relation, mapping input features to output variables. Okay, so now this is further we call this as, we refer this as hidden layer. So this expression maps the input variables or features to hidden variables, hidden outputs you can consider. Okay, hidden output. Fine. Similarly, you can see that Z is also mapped to Y. Okay, in fact, net values of Z are mapped to respect to Y by another matrix multiplication, matrix vector multiplication, right? See, what do we now mean by training of this neural network? Training of this neural network now means that we need to identify appropriate weight vectors. This W, okay, this W. So in general, how do we denote this is W? See if this HX. So that is the hidden variables are mapped to input variables, right? So I can denote this as WKZ, where K refers to the corresponding, say, XK, okay, is mapped to YZ, right? Or XI mapped to YZ. So it is WJI. We can write it as WJI. XI mapped to YZ, right? So now the training of network means how do we set all the respective weights and biases, okay, in a network. WJI, okay, and similarly WJK. Set WJI and WKZ. That is what? These are nothing but the weights connecting each of the layers. Okay. So how do we set them? Set or train? Learn to set these weights, right? So that is referred to as training of a neural network. See, in this example, we were given initially what weights to be used for each of the layers. Okay, but who will provide this information? In real situations, we will not be given the weights and the biases. Okay, weights means weights includes biases as well. Weights and biases. So how do we set them? Okay, the connection weights and the biases between each layer to the subsequent layer, how do we figure them out? Okay, or how do we learn them such that all class 1 samples go to the class 1 and all class 2 samples get classified to class 2. Okay, so how do we do that? That is referred to as learning a neural network. In the next class, let us see how do we learn a neural network. So previously we have seen through perceptron learning, how do we learn a single neuron to figure out a decision boundary which will separate class 1 and class 2 samples when they are linearly separable. Now we pose this problem. At that time we have posed this, we have formulated a cost function and we have identified the respective weight elements. Now there are several weights. So instead of weight elements, now we have weight matrices, okay, from layer to layer. So this will have a weight matrix WJI and this will have a weight matrix WJK. So all these weight matrices, these are all nothing but WJI. Connecting net J, okay, is equal to WJI into XI plus bias, right? A general equation if you want to write, this is how we write. Okay, so and summation over all Xi, 1 to D, right? Same thing if I want to write a general expression, please note that net 1 is equal to summation I equal to 1 to 3 here into W1I into Xi, okay, plus bias BI, B1, right? You can see this here. So W1I into Xi plus B. Same thing I have written in more general form here. That is, okay, net J is equal to WJI, okay, WJI into Xi plus bias, I varying from 1 to D, right? And this is the net value. And when you write this, the connection, all net J's, okay, at the subsequent layer, it formulates a matrix relation between the net values and the inputs as net equal to W into X. Similarly, there is another matrix relation that will figure out net is equal to, say, sigma WKZ into YZ plus bias. Okay, second bias of the second layer. Okay, at this layer, right? So these will form. Now, how do we matrix vector equations and learning the weight matrices now at layer to layer is of important task in learning a neural network. Let us discuss that in the next class. Thank you.